Here's a question nobody asked 30 years ago. Can a machine think? Not calculate. Not sort data. Not run a spreadsheet. Actually think. Recognize a face. Understand a sentence. Make a decision. Write a poem. For most of human history, the answer was obviously no. Machines did what you told them to do. Nothing more. But somewhere along the way, that changed. Today, an AI passed a medical licensing exam. Another one beat the world's best chess player. Another one is generating art, writing code, diagnosing cancer from an X-ray. So, what actually is artificial intelligence? How does it work? And maybe most importantly, should we be excited or worried? That's what this video is about. Let's go. Here's the roadmap for today. We're going to start with the big question. What does it even mean for a machine to be intelligent? We'll look at the history, because AI didn't appear out of nowhere, and the backstory matters. Then we'll get into how modern AI actually works. Machine learning, perception, reasoning, and neural networks. Each one builds on the last. After that, we'll look at real examples, things AI is doing right now that affect your daily life, whether you realize it or not. And we'll finish with the stuff that doesn't have easy answers, the social and ethical questions that come with a technology this powerful. This is a big topic. I'm going to give you a map, not an encyclopedia. By the end, you'll have a solid foundation, the kind that lets you follow the headlines, think critically, and go deeper in any direction you choose. Let's start at the beginning. Before we talk about artificial intelligence, we need to ask, what's intelligence in the first place? Psychologists have debated this for over a century, but most definitions agree on a few things. Intelligence involves the ability to learn from experience, adapt to new situations, solve problems, and understand complex ideas. Notice something. That's a behavioral definition. It says nothing about biology, nothing about neurons or brains. It's about what you can do, not what you're made of. That's the crack in the door that computer scientists walked through. In 1950, a British mathematician named Alan Turing, widely considered the father of computer science, asked the question differently. Instead of, "Can machines think?" he proposed, "Can a machine behave so intelligently that you can't tell it apart from a human?" He called this the Turing test. You put a human in one room, a machine in another, and a judge communicates with both through text. If the judge can't reliably tell which is which, the machine passes. It was a brilliant reframe. Stop arguing about philosophy. Just ask, does it work? Now, modern AI researchers have a broader definition. Artificial intelligence is the field of computer science dedicated to building systems that can perform tasks that typically require human-like intelligence. Notice that phrase, human-like, not human. The goal has never been to replicate a brain in silicon. It's to build systems that can do the things brains do. And increasingly, they can. The story of AI is not a straight line. It's more like a roller coaster. It officially starts in 1956 at a summer workshop at Dartmouth College. A group of mathematicians and computer scientists, including John McCarthy, who coined the term artificial intelligence, gathered with a bold prediction that every aspect of human intelligence could be precisely described and simulated by a machine. They were optimistic, very optimistic. The early years were exciting. Computers could solve algebra problems, play checkers, prove mathematical theorems. Researchers were convinced general AI was maybe 20 years away. Then came the AI winters, two major periods in the 1970s and 1980s, where funding dried up and enthusiasm crashed. The problems turned out to be much harder than anyone expected. Language, vision, common sense reasoning, these things that a 5-year-old does effortlessly were brutally difficult to program. The comeback started in the 1990s. Chess computers beat grandmasters. Machine learning started showing real results. The internet created mountains of data to learn from. And then the 2010s happened. Cheap computing power, massive data sets, a technique called deep learning. And suddenly AI went from interesting research project to reshaping the global economy. We're living in that era right now. The roller coaster is going very, very fast. Here's the thing about traditional programming. You write rules. The computer follows them. Want to detect spam email? You write, if the email contains free money in all caps, flag it. You're the one who figured out the rule. The computer just executes it. That works for simple problems. But what about detecting a dog in a photo? How do you write the rule for that? How do you describe dog in code? You can't. Not really. This is where machine learning comes in. And it's a fundamental shift in how we think about programming. Instead of writing the rules yourself, you give the machine thousands of examples and let it figure out the rules on its own. Here's the key definition. Machine learning is a subset of AI where systems learn from data and improve their performance over time without being explicitly programmed. Think about how a child learns to recognize a dog. Nobody hands them a rule sheet. They see hundreds of dogs, big ones, small ones, fluffy ones, spotted ones, and over time, their brain builds a pattern. Eventually, they can identify a dog they've never seen before. Machine learning does the same thing. Feed the system 10,000 labeled photos. This is a dog. This is a cat. This is a dog. The system learns the patterns. Then you show it a new photo it's never seen, and it makes a prediction. There are 3 main flavors of machine learning. Supervised learning. The system trains on labeled data. You give it the questions and the answers. It learns the mapping. Then it answers new questions on its own. This is like studying with an answer key. Unsupervised learning. You give it data with no labels, no answers. The system finds patterns and structure on its own. This is like being handed a pile of newspapers in a language you don't speak and trying to figure out which articles are about the same topics. Reinforcement learning. The system learns by trial and error in an environment. It takes an action, gets a reward or a penalty, and adjusts. Think of training a dog with treats. Except the dog is an algorithm, and the treats are numerical rewards. This is how AI learned to play chess and Go at superhuman levels. One of the hardest problems in AI was giving machines the ability to perceive the world. Perception for humans feels instant and effortless. You glance at a photo, you see a beach, you hear a voice, you recognize your friend, you read a sentence, you understand what it means. Under the hood, your brain is doing something incredibly complex. Millions of neurons firing, patterns matching, context loading. AI researchers spent decades trying to replicate just tiny pieces of this. Computer vision is the area of AI that deals with images and video. How do you teach a machine to see? Early approaches tried to hand-code features. Edges, shapes, colors. It worked, barely. Modern approaches use deep learning, which we'll cover in a moment, and the results are startling. Systems can now identify objects in images more accurately than humans. They can read text, recognize faces, detect tumors in medical scans. Natural language processing, NLP, is the area dealing with text and speech. Human language is a nightmare for computers. It's ambiguous. It's full of sarcasm, metaphor, context, and cultural references. I saw the man with the telescope. Did I use the telescope, or did the man have it? Humans parse that instantly. Computers struggled with it for decades. Modern NLP has made extraordinary progress. Voice assistants understand you. Translation tools convert between languages in real time. Language models can read a document and answer questions about it. The key insight behind modern perception systems: don't try to hand-code the rules. Let the machine learn them from massive amounts of data. That shift, from rules to learning, is the thread running through all of modern AI. Perception is about input. Reasoning is about what you do with it. Humans don't just recognize things, we think about them. We make inferences, we plan. We solve problems we've never seen before. We apply knowledge from one domain to another. Can machines do that? Early AI was almost entirely about reasoning. Researchers built systems called expert systems in the 1980s. Massive rule databases that encoded human expert knowledge. A medical expert system might have thousands of rules. If the patient has a fever and a rash and has traveled to these regions, consider these diagnoses. They actually worked pretty well in narrow domains, but they were brittle. Step outside the rules, and they fell apart. They had no common sense, no ability to handle situations they hadn't been explicitly programmed for. Modern AI reasons differently. Instead of rules, it builds probabilistic models. Models that assign likelihoods to different outcomes based on patterns in data. It doesn't say, "This is a dog." It says, "I'm 97% confident this is a dog." That might sound less impressive, but it's actually more honest. And it handles real-world messiness far better than rigid rules. One active research frontier is something called general reasoning. Getting AI to solve problems it has never seen before, transfer knowledge between domains, and handle the unexpected. This is where AI still struggles compared to humans. A child can understand "don't touch the hot stove" and immediately generalize "don't touch other hot things." AI systems are still working on this kind of flexible, transferable reasoning. Okay? This is where it all comes together. Because if machine learning is how AI learns, neural networks are the machinery doing the learning. Let's start with biology, because neural networks were explicitly inspired by the brain. Your brain has roughly 86 billion neurons, nerve cells that receive signals, process them, and fire signals to other neurons. A single thought involves millions of neurons activating in patterns. Your ability to recognize your mother's face, understand a joke, remember a song, all of it emerges from these simple cells connected in extraordinarily complex networks. In 1943, two researchers, Warren McCulloch and Walter Pitts, proposed a mathematical model of a neuron. A simple on/off unit that takes inputs, applies weights, and produces an output. One artificial neuron isn't impressive. But connect thousands of them together? Something interesting happens. An artificial neural network is a system of connected nodes organized in layers, inspired by the structure of the brain, but simplified. Here's how it works. The input layer receives raw data. For an image, that might be the value of every pixel. Hidden layers in the middle transform the data. Each connection between nodes has a weight, a number that says how important that connection is. During training, these weights get adjusted. The output layer produces a result. Dog or cat. Spam or not spam. A number. A word. Training adjusts the weights using a process called backpropagation. The system looks at its error, traces backward through the network, and nudges every weight slightly in the direction that reduces the mistake. Do this millions of times with millions of examples, and the weights slowly encode the patterns in the data. Deep learning just means neural networks with many hidden layers. Deep refers to depth. More layers let the network learn more abstract features. Early layers might detect edges in an image. Middle layers detect shapes. Later layers detect objects. The deeper the network, the more complex the patterns it can learn. This is why modern AI can do things that seemed impossible 10 years ago. Image recognition, language translation, voice synthesis, drug discovery, game playing, all driven by deep neural networks trained on huge datasets with enormous computing power. One important caveat: neural networks are powerful but often mysterious. We know they work. We often don't know why they produce a particular output. This black box problem is one of the biggest challenges in modern AI, and it connects directly to the ethics we'll talk about shortly. Let's make this concrete. When you open Netflix, you see recommendations. Not random ones, ones that feel weirdly accurate. Behind that is a recommendation system built on machine learning. Here's the simplified version. Netflix collects data: what you watch, how long you watch, when you pause, what you rewatch, what you abandon after 5 minutes. It also knows the same data for millions of other users. The ML system finds patterns. People who watched X, Y, and Z also tended to love W. You watched X and Y, so the system predicts you'll probably like W and surfaces it for you. No human told it Glenn likes slow-burn thrillers. The system inferred that from behavior. That inference is machine learning in practice. The result? Netflix reports that over 80% of content watched on the platform comes from these recommendations. That's not coincidence. That's a well-trained model shaping what you watch. Here's an example with higher stakes. Diabetic retinopathy is a condition where diabetes damages blood vessels in the eye. Left undetected, it causes blindness. Detecting it requires a trained ophthalmologist examining a retinal scan. And there aren't enough ophthalmologists in the world to screen every diabetic patient regularly. Google trained a deep learning model on over 128,000 retinal images, each labeled by certified ophthalmologists. After training, the model was tested on new images it had never seen. The result: the AI matched or exceeded the accuracy of human ophthalmologists in detecting diabetic retinopathy. In seconds, at virtually no cost per image. This isn't replacing doctors. It's extending their reach. A model like this, deployed in rural clinics without specialist access, could save millions of people's eyesight. That's perception, computer vision specifically, solving a real human problem at scale. You've probably used a large language model. ChatGPT, Claude, Gemini, they're everywhere right now. So how do they actually work? At the core is something called a transformer, a type of neural network architecture introduced in 2017. Without going too deep, transformers are extraordinarily good at understanding context in sequences of text. They don't just look at one word. They look at how every word in a sentence relates to every other word. Training a large language model works roughly like this. Take hundreds of billions of words of text from the internet, books, and other sources. Train a neural network to predict, given these words, what word comes next. Do that trillions of times, adjusting weights each time. The model never memorizes facts exactly. Instead, it builds a rich statistical understanding of language, how words relate, how ideas connect, how arguments are structured. The result is a system that can write essays, answer questions, explain code, summarize documents, and hold conversations, not because it was specifically programmed for any of those tasks, but because it learned the patterns of human language at enormous scale. It's still not reasoning the way humans do. It can make confident-sounding mistakes. But it's a genuinely new kind of tool, and understanding it is increasingly part of basic technological literacy. Here's where we need to slow down and think carefully. Because powerful technology always creates hard questions. Bias in AI. Machine learning models learn from data, and human-generated data contains human biases. Hiring algorithms trained on past decisions have been shown to penalize resumes with women's college names. Facial recognition systems perform worse on darker skin tones because training datasets had fewer examples of them. The model learns what it's taught, including our mistakes. This matters enormously when AI is used in hiring, criminal justice, loan approvals, and healthcare. Bias in the data becomes bias in the decision, and automated bias can scale faster and wider than human bias ever could. Privacy and surveillance. AI makes it possible to track, identify, and monitor people at scale in ways that were never before feasible. Facial recognition in public spaces, behavioral tracking online, predictive policing systems. Each of these has genuine use cases and genuine risks to civil liberties and privacy. Who controls these systems? Who oversees them? What are the limits? Jobs and the economy. AI automates tasks, and that changes work. Some jobs will be displaced, others will be augmented. Entirely new categories of work will emerge. Economists debate the net effect, but there's wide agreement that the transition will be uneven, hitting some workers and industries much harder than others. The autonomy question. As AI systems make more consequential decisions, medical diagnoses, parole recommendations, financial lending, we face a fundamental question. Who is accountable when they're wrong? The engineer who built it? The company that deployed it? The AI itself? We don't have complete answers to these questions, but they're not optional. A society that deploys AI without grappling with these questions is one that cedes control of its future by accident. The good news: these are human problems with human solutions. They require policy, ethics, transparency, and democratic debate, not just engineering. All right, let's bring it all together. Intelligence and machines. Intelligence is behavioral. What a system can do. The Turing test asked not, can machines think, but can we tell the difference? AI aims to build systems that perform tasks requiring human-like intelligence. Machine learning. Instead of programming rules, we feed systems data and let them find patterns. Supervised, unsupervised, and reinforcement learning are the three main approaches. Perception. Computer vision and natural language processing let machines see, hear, and read. Modern perception systems are trained on massive data sets and are now competitive with, or better than, humans in specific tasks. Reasoning, from rule-based expert systems to probabilistic models, AI has moved toward handling uncertainty and ambiguity. General, flexible reasoning remains an open frontier. Neural networks and deep learning, inspired by the brain, neural networks use layers of connected nodes trained through backpropagation to learn complex patterns from data. Deep learning is the engine driving the modern AI revolution. The ethics, bias, privacy, labor displacement, and accountability are not afterthoughts. They're central questions that engineers, policymakers, and citizens need to answer together. Here's the thing I want to leave you with. AI is not magic. It's math, data, and computing power. Built by people, for people, shaped by choices people made. That means it can be built badly or well, deployed responsibly or recklessly, used to concentrate power or to distribute opportunity. You're studying computer science at exactly the moment when these decisions are being made. That's not a small thing. The people in this field, the ones who understand how these systems work, what they can and can't do, and what questions to ask, those are the people who will shape what comes next. That might be you. If this video helped you, drop a like. It seriously helps more people find this content. Subscribe for more CS 101 lessons, and leave a comment. What part of AI are you most curious about? Or most concerned about? Both answers are welcome. See you in the next one.